tested?
I think so. I think I'm ready.
Okay.
Maybe, probably not. Okay, so we're basically going to extend what we did in class today, but instead of finding the mass where we had to like find the potential energy and then basically subtract the mass of each individual like neutron and proton, we're going to just find that change in potential energy. So, or this change in potential energy. So the first thing that we want to do is just find this change in potential energy from each individual proton and neutron coming together. But instead of it being in kind of a blob or a sphere that would normally happen, we're simplifying it for it to be in a line, so we know exactly how many bindings basically we have. So to determine which of these will undergo that strong nuclear force and release that potential energy per binding, we're going to use the range of that force to be 2.1 whatever Phsx. I'm going to call them Phsx because I have no idea what those are. I don't know. Does anybody know what the actual thing is?
Fermi.
Fermi's is.
I don't know what it means, but I know.
Well, I mean, it's something. It's something short for something meter. It's literally the thing smaller than picometer, which is the smallest thing I ever learned. So, so the range of this strong nuclear force is going to be 2.1 Fermis, basically just so we know to include everything 2 and less. And then each nucleon's diameter is 1 Fermi. So basically, the distance between these two is going to be 1 Fermi, and the distance between like these two will be 2, because they'll be as close as possible. And also kind of notice that I've arranged these so the protons are as far apart as possible. And that's intentional because the proton should be as far apart as possible to reduce the amount of electrical repulsion. But we're not going to worry about electrical repulsion yet. We're just going to first find the energy released by binding these things together in this line like this. So we just have to determine how many bindings we have. So I'm going to erase this so we can determine how many bindings we have. So this one here is going to bind to 1, 2, and then this one obviously binds to this one, but also this one, and this one. And then this one will bind obviously to that one, this one, and to this one. And then this one will bind to this one, and that one, and this one, and that one. Or count these up. And then this one will also go to this one, and then also the last one. Okay, so let's count these up. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So maybe I see one I missed just in case I haven't done this all the way through yet. But I'm pretty sure that's all of them because everything's bound to the thing next to it, the one 2 away from it. Okay, so that is 9 total bindings. That's what I'm going to call it. 9 bindings. Okay. So each one of those bindings is going to have a change in potential energy of 3 mega electron volts per binding. So all we have to do to find this change in potential energy is do that 9 bindings times 3 mega electron volts. I think you guys can figure that. That's 27 mega electron volts. This way, see if yeah, okay, so 27 mega electron volts.
Can you go over how you
did yeah, okay. So basically I just did whichever one, I just counted a binding as anything that was within 2 Fermis. Okay. And since each one's technically 1 Fermi away, then I just did the one that's next to it and then any of them that are 2 away from it. So the 2 closest to it. Okay. So like this one, let's start with this one. So like this one will be bound to this one, this one, this one, and this one. And those are shown by 1, 2, 3, 4, and yeah, 4. That should be 4. Okay. Does that make sense? And then each one, as far as I know, is bound to every one too. So 1, 2, this one's bound to 1, 2, 3. This one's bound to 4. This one's bound to 4. 1, 2, 3, 4. This one's bound to 3, and then this one's bound to 2. Make sense?
Not quite. I'll figure it out.
Okay, we'll talk after class. It's fine. So 2. Oh, did I count all of them right? I think so. Yeah, I did. Yeah. Okay. So that should be right. So, yeah, that's right. Okay. So 1, 2, 3, 6, 7, 8. Okay, cool. So it's good. So we found 27 mega electron volts, which is a lot of energy. So great stuff. So now, what we didn't do in class is actually adjust it for the fact that the protons do have a repulsion force between them. And so we're going to adjust for that now. And the way we're going to do that is by assuming that the electrical repulsion is going to be 1 mega electron volt per Fermi. Okay. So if it's 1 Fermi away, basically if it's 1 Fermi away, then it'd be 1 mega electron volt divided by 1 Fermi would be 1 mega electron volt of repulsive force. If it was 2 away, then it'd be 1/2, 3, 1/3, yada yada yada. And each one will have an effect on the other one. So these two will repel, these two will repel, and these two will repel. So we have to take in all of this to account. So these two are 2 Fermis away, whereas these two are 2, 3, 4, 5 Fermis away, whereas these are 3. So 2 away on the left side, 3 away on the right side, and then the ones on the ends are 5 away from each other. So for the adjustment, I'm just going to do electrical repulsion as ER. Is just going to equal all of these added up. So the 1 mega electron volt divided by 2 Fermis plus 1 divided by 3 plus 1 divided by 5 equals, I'm not 100% sure, 0.2 plus 533 plus 1. Yeah, it's going to be a little over 1, I think.
Do you want to get my calculator out?
Yeah, sure, that'd be nice. I have time to do this beforehand. So 0.5, 0.7, it'll be like 0.1 or 1.033 or something like that.
So we only look at the protons?
Yeah, because the neutrons will not repel because there's no electric. They don't have any. They don't have any charge, but the protons do. Yeah, so we only look at protons. The neutrons are basically there to ensure that they bind together. Which
1.0, yeah. How
1.0
did you do that in your head?
I did. I took the time to do it. So there's 1.033 mega electron. So that is the repulsive force. So to find out the energy released, just equals that 27 mega electron volts from the change in potential energy minus that the repulsive binding or repulsive electrical force. So you end up with 25 point something. 25.97. Okay, so 25.97 mega electron volts. And so that would be the amount of energy you'd get if you took all of these individual nucleons from some distance far away, and then kind of put them together in a line and force them to bind in a line like this. Okay? Makes sense? So, yeah. So that's important. So yeah, Yeah. So basically, all we did in class today was this part, but then there is electrical repulsion that you shouldn't ignore unless he tells you
That
to.
whole thing, that whole lecture was about that.
Yeah, no, he lectures a really long time.
Me and Garrett didn't do anything today. We just sat there.